All right, good afternoon. Let's get started. Hopefully we can get you out of here a few minutes early. All right, so last time we talked about the stress in a beam, right? So we talked about the situation when you have an only movement there. We call it, you remember, there is only movement, no shear force. We call that situation no shear, only bending movement. Pure bending, right? We call it pure bending. So when there is a only bending moment, pure bending, we talk about there will be stress, only normal stress, axial stress, or bending stress. That means right, the same situation here. Okay, so the bending stress will be distributed in the beam, and then the maximum will be at either the top or bottom edge of the beam. And for that, we can actually determine, use the section modulus. And to determine, you find out the maximum moment, then divide the section modulus, will give you the maximum stress. Right? If you multiple locations, then you have to compare, take whatever the maximum one, right? The real maximum. Okay, so that's for bending stress. Now, the next question we're going to answer today is, what if it's not pure bending, right? So let's say you have a beam like this one I show here, right? If you have just a simple beam, instead of pure bending, now you have a force applied in the middle. Now we know this one you have going to have a shear force in the beam, right? Anyone remember the shear VM diagram? Anyone remember the VM diagram for this one? Why we're saying the shear? What's the reaction here? Oh. Okay, what's the reaction force here if I apply P here? Half P, right? Half the load. Oh. All right. And then this will be half P. Okay, so what's the V diagram? If you draw V, what's the V diagram? You start zero, jump up half P, and then you constant in the middle, you see a counter force, so you jump it down P, and then negative half P continue until the end. Now in this beam, there are always shear force there. So it's not pure bending. Right? So in this situation, what kind of stress you're going to have? That's what we try to answer today. Okay, so first observation. Okay, if you have let's say like a two beam, you can put the two bars together as a beam, or you can just hold your notebook, right? There are many pages here. There are many layer of beam. Now if you bend it, if you look at this side here, this thing kind of become not intact anymore, right? Not a straight line anymore. So it will be some deformation. They will stick out, separated, right? Actually, you can go home, try something. Put some ink or something here, right? And then you bend it. Okay. See if that thing gets spread out because of the bending. If it's spread out, that means they're sliding against each other. That means shear, right? So that's an indication there's shears between the layers. Right. Okay, so in this case, for example, we have two layers. You can see the two, look at the end. They're not plane anymore. There are some stretching right apart. That means there was shear deformation. So in general, if you have a beam that under shear force, right, and also under bending moment, then there will be a shear deformation, shear stress. Right? Okay, so we need to look at, in this kind of beam, what's the normal stress and what's the shear stress. Okay, so the normal stress, okay, the approach is we'll use the same equation we had before. We just use sigma equal to m, right, y over I. That's how you calculate the stress. But in addition to the shear normal stress, you're going to have a shear stress top. So we need to find out how to determine the shear stress in a beam. All right. So before we actually find it, let me kind of explain, give you a physical understanding or feeling what's going on, give you some of the general picture. Okay. So when you have a beam like this one, right? So if you draw the VM diagram, okay, let's continue draw the VM diagram. Remember, we need a VM diagram, right? That will be some homework problem, right? Okay, so what's the M here in this same beam? Star 0, accumulate positive area, right? And then you accumulate negative area. So straight line, that's all straight line, right? So it's like a triangle, go up and down. Now in this beam, now you can see the moment is changing everywhere from this point to next point, right? So it's a changing, it's a variable, right? So moment is changing. If we calculate the stress this way, what does that mean? That means at different location, you're going to have different stress. Even if you have the same Y, if you look at the same layer, same Y value, your stress is going to be different, right? Is that true? Because according to this equation, the stress is determined by M, Y, and I. So if you're giving the same layer, same Y, but the moment is changing from this spot to the next spot, then your stress is going to be changed. Right? Okay, so that's one observation. All right. Second, if let's say we look at this beam, there is a shear, right? So if we look at the beam, let's say I cut the element out. Okay. In pure bending, you have only bending moment here. Now, in general, in this situation, when there is a shear force, we know there will be a shear force here, right? Remember sign convention here, this is the positive, this is the positive, so you have a pair, right? So you're going to have a shear force, right? Okay, now there's shear force. Now, this is a force. This force will be distributed on this cross-section. Some way of distribution, right? Either uniformly or not uniformly, but it will be distributed among this cross-section because it cannot be just one point. So you're shearing this cross-section. There is a force V. We call V. V is not 0 in this case, right? Okay, so there must be a shear stress, right? Let's say we just don't know yet. Let's say we just give a sign, call it a tau. So let's say we look at this spot here. Okay, I'll just draw this spot, put it here, make it bigger again. Right? So there must be a shear stress tau. We don't know the value yet, right? On this side. And then, of course, on this side, you're going to have a shear. Must be a pair, right? So maybe this way, if you're on this. Right? Actually, in this case, because V is pointing downward here, so this side should be, should be this way. So this side is, the tau should go this way. And then this side, the tau is this way. Right? So I'm just randomly pick a small, tiny location element out. That's the situation. Now, this is not in equilibrium, right? Is this in equilibrium, this element? It's not, because you have this tau, this is all in equilibrium. Sigma Fy equals 0. But it's a spinning moment, right? This is a pair, right? It's a couple. So that couple generates moment. The moment is this way. So it's not in balance. Therefore, that moment, that element, the tiny spot you move, you basically try to twist this way. Right? But this is in equilibrium. And there is material on top of it. So the material on top of it will be resistant to this move. Therefore, you have a reaction, another right, shear stress here. And similarly, you have another shear stress here. These two must be same value, opposite direction, because the sigma fx must be 0. And also the two moments generated by these two pairs must be in balance. So therefore, what you have here will be tau as well. Here will be tau as well. Right? So for this reason, if you have this cross-section, there is shear stress, then between the layers, there must be shear stress. Right? Otherwise, you cannot be in equilibrium. Okay, so that's just a physical understanding, right? Okay, how much is the value? We will find it out next. I'm just saying there must be shear stress. Okay, everyone accept there will be shear stress? Okay, now I want you to look at this spot here. Another special point, the very top tip there. Okay, on this tip here, okay, let's draw this picture here. So this block, right? Okay, for this block, what's the shear stress on the top surface? What's the shear stress on the top surface? 0. There's nothing there, right? It's free. So this tau will be 0 here. Okay, on this surface, it's 0 here. Now, this is 0. So sigma fx must be 0. So what's the shear stress here? 0. Okay. Now this, what about here? What about here? They all must be 0. Let's say you have one that's not 0, then not in equilibrium, right? So for this element here, the shear stress must be 0. I mean for the tip, the edge, right? Same reason for here, the shear stress must be 0. Yeah.
But the part of the block under that one,
Mm-hmm.
the shear stress, right?
Yeah.
So why wouldn't it affect, like piece of paper?
Yeah.
Why wouldn't
Yeah. They will be. Yeah. I'm looking at the two locations. One not 0. Here is 0. Okay. Now how can that happen? There must be some change. That gradually from 0 they gradually increase. Then you'll be okay. Right. So the point I'm trying to make here is, okay. First, there must be shear in all the, horizontal direction and also vertical direction. That's point one. Secondly, the shear stress is not uniform. Right, on the cross section. See, at the very top, it must be 0. In the middle, we know it's not 0. So therefore, it's not uniform. Therefore, you cannot calculate the shear stress this way. See, V divided by cross-sectional area. You cannot, right? Because the shear is not uniform. So we have to find another way to find out the shear stress. That's the point. All right, so next we'll say, how can we find out the shear stress? Okay, the way we can find it is actually illustrated here. Okay, let's say in general we have a beam that under both moment and the shear force V, right? Okay, so that's the element. So we can pick out an element, this element dx here. Right? If you draw the free body diagram, equation of equilibrium, right? Free body diagram, you can see here. Right? On this side you have V, then you have M. Now on this side, you can have a different V in general, and you can have a different M in general, right? Because M going to change because the dm change equal to the slope equal to V. V is now 0, therefore M from the left side to the right side must be different. Right? Remember this equation, dm dx equal to V. So if V is now 0, M must be changing. Right? So it's not pure bending. Pure bending situation, V equals 0, and then you have M is same everywhere. But this situation, V is now 0, so M must be changing. Okay, remember that in mind. Okay, now if we cut this element out, if you look at this picture here, okay, the next picture. So we can draw it. Okay, so here will be normal stress, and then there must be shear stress here as well. Right? So the shear stress, we don't know the value yet, but there must be shear stress. And this shear stress is changing with location. So you should write it as, what we should write it this way, tau as a function of y. So changing depending on the location. Right? So that's the picture look like. Okay, now how to find it? For this whole thing, if you want to write the equation of equilibrium, it's hard to find it. Okay, so the way we can find it is actually look at this block. Cut the top portion of this element. Okay, the reason I wanted the top portion because I know here it's 0. At the very top, I know that surface, there's no shear stress. Right? So I can cut this block, take it out, and that will give me this picture here, shown in figure C. Right? Okay, so now I take this picture, take this block out, and I cut this is a free body diagram. Okay, free body diagram, therefore I draw the free body and then label all the forces. And in this picture, actually, I just label all the stresses. Right? So you're going to have shear stress here, and shear stress here, and the shear stress at the bottom here. Right? Is that correct? You all accept that, right? So you're going to have stress. Why you have stress sigma 1, sigma 2? Different. Because the moment is different. Remember, sigma calculated by moment times y over I. So now on the two sides, you have different m. Must be different stress. So we call one sigma 1, then the other one will be sigma 2. Right? Okay, we'll find it what's the value next. But in principle, two sides you have different. Okay, now let's use this block, write the equation of equilibrium. Okay, to do that, we have to calculate the forces. The equation of equilibrium is about the forces. It's not about stress. So to get the forces, you have to use stress times the area, right? Okay, so here is what we get. Okay, so you add all this together. The left side, you're going to have a force F1, right? Because you added them together, you have F1. And then on the right side, you're going to have F2. Actually, here you're going to have a shear, some kind of shear force. And here you have some, I think it's, this side is this way, this side is this way. So you have a shear force, right? So that's all supposed to be the completed free body diagram. Now, our task is we try to find out what? We try to find this force. Because this force is related to the shear stress here. Right? Okay, so we know actually sigma 1, sigma 2, because we know moment. So we know the F1, F2. We just need to find out F3. Now, what's the equation we can use to find out F3? For this free body diagram. Should be sigma fx equals 0, right? Okay, sigma fy doesn't matter, right? So we don't care, so we just need to find F3. So therefore, sigma fx equals 0, right? Okay, remember that sigma fx equals 0. Now write it out. That's what you get here. Okay. So the first one, this part. What is this one? This is the F3, right? Okay, how you determine F3? Should be stress times the area, the bottom area. Okay, what's the size of bottom area? Should be dx times the width or the depth this way. That's the b, right? And this one dx, b, and then times the top. That's the F3, right? Okay, now what about this F1 here? The F1 here. It's supposed to be sigma 1 integral over this area, right? So that's what you have here. Sigma x integral over the area A. Okay. Now what's on the right? Should be the sigma changed, sigma 2, right? Over the area. So therefore, that's the sigma fx equals 0. Right? Okay, next just derivation, all right? So you just plug in the equations. Okay, we combine these two terms together, you get this equation. And then I move this side, this one, to the other side, so I get this equation. The tau equals that. Okay, now for this, because I know the equation for sigma at this location, sigma at this location. So I combine them, give me this equation. Right? Remember, sigma x equal to m at the location x, then y over I. So therefore, this difference will be the moment change, moment difference. Right? So therefore, delta sigma x will be delta m, and that's this equation. All right? Okay, next will be much easier. You just combine the terms. Right? Here you have this b times dx. You just divide it over, so that move it to the other side, and you will get this equation. So now we have an equation. You can determine the tau. Okay, what's the q here? Q is actually this term. You actually, because the integral here, remember this dA, you go from y, right? This is location y here. From location y to the top. That's why you have integral from y to half h. Right, so that's the integral. Okay, how to calculate, that's next. But at least I can write this expression, right? So the tau, the shear stress, will be V times Q over I and B. Okay. All right, any questions here before I move on to find out what's the Q actually? No question? All right, okay, now let's find out the Q. Okay, Q is, we define, based on this derivation process, we define as y integral of this dA, of this area. That's the one from the top to your location y. Okay, so therefore that's something depend on geometry again. Has nothing to do with load again. Right. Okay, so when you have different shape of beam, the Q value will be different. The simplest one, the easiest one you can calculate is when you have a rectangular beam. I mean the cross section is a rectangular shape. Okay, in this case, here is the derivation. All right. So you go from this location y to half h to here. So you basically calculate the shaded area at the top there. Do the integral. So you put it here, y, right? That's what you want to calculate. And that dA is actually b times dy. Right? It's the width of the beam times the small tiny dy. You all add them together. Okay. So for that reason, b is a constant. You can throw out, and then you calculate the y dy integral. That gives you y squared. So you get this equation. So therefore, for rectangular beam, the Q expression is actually very simple. It's a parabolic shape. So let's go. All right. So put that in, you get this tau. All right. Now, if you look at here, look at this equation. That should be one equation on the formula sheet, right? That's the way how you determine the shear stress at location y1. All right. Okay. What kind of distribution is this shear stress? If you look at this equation, parabolic, right? Y squared. Okay. You just silent it. Right. Okay. So this is a parabolic curve, right? So if you plot it, this is the shape you'll see here. So the shear stress, right, will be a parabolic distribution. Maximum in the middle. 0 at the tip. So it's 0 here. That conform we just showed in the last slide, right? So at the tip, shear stress is 0, but it's a maximum in the middle. So interestingly, when you have a beam, the maximum normal stress always at the top or bottom, but the maximum shear is in the middle. So for a beam to be strong enough, you want to put a lot of material. You want your top and the bottom, put a lot of material there, strong, to against the bending. But also you need to put some material in the middle to against the shear. So you cannot build a beam without material in the middle, because then the little bit shear, it will be failed. So there's nothing against the shear stress. So that's why the I-beam is actually very popular or very efficient design for use. Because this way you put a lot of material here at the top and bottom against the bending. But also you have this part here in the middle against the shear. Right? So it's the best use of material. Right? Because it's better than a rectangular one. If you have a rectangular one here, you have lots of material put there. For the I-beam, you take away all the material here, all the material here. Right? So you save a lot of material at about the same strength or same stiffness against the bending. All right. Okay, so this is parabolic. Now quickly, what's this maximum value? What's this value here? Can we determine the maximum value? Yes, we have the equation, right? So just find the maximum. You can do d tau dy1 equals 0, find where the maximum is. Or you can just look at the equation here. This is a something square, a squared minus b squared. So what b value, this equation is maximum when b equals 0, right? Your a squared minus b squared. When b is the smallest, this whole thing is the biggest. So therefore, when y1, smallest one can be 0, right? Because if it's negative, then it's square is positive value again. So the maximum you can, minimum you can go is 0. So therefore, when y1 equals 0, that's right in the middle, and you're going to have the maximum. Okay, put this y1 equals 0 in there, you get this expression. And this expression, you can simplify. It's actually this value. Okay, what I simplified? Anyone realize what I simplified? What's the a here? It's the cross-sectional area. So it's basically the area. Okay. And here, actually, you can see the maximum shear stress is 3/2, 1/2 of V over A, right? So it's not equal to the V over A. Now you see again, it's not uniform, right? So you cannot calculate using V just divided by A. It's actually 1.5 times bigger than this at the middle, but it's 0 at the bottom and the top. Okay, so in summary, this is the equation we need to calculate the shear stress. Any questions here? No question? Or you all fall asleep? All right. Okay, if no question, let me just show a few pictures, just help you visually see what kind of shear stress you're going to have in a beam. All right. So just for fun. All right. So now this is a beam. Okay. So if you have a long beam and there is a shear force in the beam, right? So then you can see here how the shear stress is distributed. So at the very top, 0. There is no, say, basically the length of the arrow kind of representing how big the shear stress is. Right? So at the very top, 0, nothing there. At the very bottom, 0 there. And then if you go from the edge, the top edge, inward to the center, okay, gradually have some error there, and the error gets bigger, and then the biggest in the middle. So that's the shear, how the shear stress is distributed. Right. Of course, you can show it this way. Use this figure here to show the magnitude. It's maximum in the middle, smallest. Okay. So we need to keep in mind this very important concept. Shear is maximum in the middle, and then the normal stress are maximum at the edge. Okay. Don't get this too confused. This is a very basic concept. You can say, I forget all the equations, I forget how to calculate. That's fine. But you should not forget this image, how the shear is distributed there. All right. Okay, so that's just to show it. Okay, now if we cut a local element out, we cut here. Okay, so if you cut here, this element there, that's the kind of shear stress distribution on that small element. Okay, so under the edge, you have the shear there, right? This is basically the cross section of the beam. You have the on this side shear stress going this way. Of course, depending on the V direction, if it's positive V or negative V, right? But in this case, it's going downward, and then on the left side, go upward. But the top surface, you see, it's going this way, right? And then the bottom system must go down. So on this element, there must be four sides, all shear stress there. Okay. So that's what I just said. Efficient use of material is use IV. Okay. So here is actually when you bend a beam, all right? So the deformation actually will be look like this if there is a shear. Because shear, remember when you look at this one here, in the middle you have very big shear, right? So what the shear does, shear generates a torsion, right? So with that torsion, actually maximum in the middle, but at the edge, it's actually 0. So the maximum, the middle part, if you look at the element here, this one won't be remain as a square anymore because of shear. But if you cut the element here, it will remain as a square because there is no shear. Right? So therefore, when you have a beam under this load with shear, and that's actually the kind of deformation you're going to get. That's the M1 to N1, the shape. So you don't have the plane assumption anymore. So when you bend a beam with shear, okay, the plane assumption is not true anymore. Right? Because the middle part, it twists more, and the edge, it twists 0. So therefore, it won't remain as a plane. Right? So that's a general conclusion. However, in this class here, or in the small deformation range, oftentimes when we do the calculation, we kind of ignore this shear deformation. So we still approximately treat it as all plane remain as a plane. So we are still using this equation to calculate the normal stress, mi over I, to calculate sigma x. Remember, this equation was derived based on plane assumption, right? Now you say in general plane assumption is not true. Why can you use this equation? Because this shear is actually very small. So we kind of ignore it. So we remain assume that the plane assumption is still true, and we can still use the same equation to calculate normal stress. All right. So in the beam, now we have two equations. One to calculate the normal stress, or the bending stress, sigma x here. And then one is the shear stress equation. You can calculate the shear distribution in the beam. So problem-wise, actually, it's pretty straightforward. You just use the equation, determine the stresses. Right. And so the key will be determining the maximum M moment. You need a VM diagram, figure out where the M is maximum, and then where is the maximum V. Then you use that value to determine. So the calculation actually is pretty straightforward. All right. Okay. I think that's basically the content I want to cover today. Any questions? All right. So there are homeworks there already assigned. It will be due next week, the week after spring break, right? So try to work on. Okay, if not, have a good, safe spring break. All right.